We've all heard that like charges repel and opposites attract, but how do charges really work? Charge, like mass, is what's known as an intrinsic property of an object. It's a fundamental property to the object that we can measure. However, unlike mass, an object can either have a positive or negative charge, depending on how many protons or electrons it has. Another property of charge is that it's quantized, or always shows up in multiples of one elementary constant. The elementary constant is equal to the charge of one electron or one proton, which has a magnitude of around 1.61 times 10 to the negative 19th coulombs. Finally, like mass, charge in object interactions is conserved. This means that if two objects that allow charges to move freely, or objects called conductors, are placed in contact with one another, the total charge of the two objects must stay the same. So, like we've heard before, like charges repel while opposite charges attract. The magnitude of this electrostatic force is given by Coulombs Law, or F equals K Q1 Q2 all over R squared. Now, while we touch on this formula in AP Physics 1, it's important to get used to a different form of this equation, where K is equal to 1 over 4 pi times epsilon naught. Epsilon naught is what's known as the permittivity of free space, and it'll be used in many other places throughout the E&M semester. Another thing that helps me understand the electric force better is to think of it kind of like a backwards gravity. We can see an extremely close resemblance between Coulombs Law and Newton's universal law of gravitation, only replacing mass with charge and capital G with 1 over 4 pi epsilon naught. In addition, while two positive masses attract each other, two positive charges actually repel each other, but the way these forces act is surprisingly similar. This analogy helps us to look at a topic that's new to AP Physics C, the electric field, whose definition is given by the force on a positive test charge divided by the charge itself. Like gravity, these vector fields are what produce the interaction forces between two objects in space, and we depict electric fields with arrows that point away from positive charges and towards negative charges. Using Coulombs Law, which calculates the force between two point charges, we can use our electric field definition to get an equation for the electric field due to a point charge, or E equals 1 over 4 pi epsilon naught times Q over R squared. Now, theoretically, we can integrate the infinitesimal electric field contributions over a surface or line of charges to calculate the total electric field at any given point. For example, let's take a look at an infinitely long line of charge with linear charge density lambda and see what the electric field due to this line of charge is at a distance r away from it. Taking an infinitesimal charge to be lambda dl, or an infinitesimal length of the line times the charge density, and making use of symmetries to cancel out the horizontal electric field contributions by each tiny piece of charge, we can integrate using our original formula to get the total electric field. You can technically use this technique to find any electric field, but there are much simpler equations like Gauss's law that will be discussed in future videos. Another field that charges create that's similar to gravity is a potential field. Like gravitational potential and gravitational potential energy, electric potential is a scalar field and measures how much electric potential energy a charge would have based on its interaction forces. And the change in electric potential can be calculated by integrating the negative of the dot product of the electric field over the path taken through this field. Taking a look at our electric field equation due to a point charge, we can go through this process to arrive at an equation for the electric potential due to a point charge, or V equals 1 over 4 pi epsilon naught times Q over R. Now, there are countless equations for different geometries of charges and their electric fields and potentials associated, but we will need to discuss an equation called Gauss's law in the future to learn more about these in depth. For now, you can feel good that you just finished learning about charge, Coulomb's law, electric fields, and electric potential.